Mark Wanger, Director of Application Development for QCI, and myself, Steve Reinhardt, VP of Product Development. So today we'll show you two practical demos of how to solve real-world constraint optimization problems using quantum computers. And that is our first goal for this webinar. The second is to identify some of you who need that capability, but you need the power of quantum computers, but you don't have the time to learn the intricate details of programming quantum computers at a low level. So I'll give a brief overview of Mukai. Raouf will give a demonstration of our constraint optimization API. Mark will work with some problems in our community detection capability. And then we'll have Q&A at the end. And please feel free to put questions in the chat at any point, and we'd ask you to keep verbal questions until we're done. And we expect to leave about half the time, half of the hour for that. So jumping into Mukai overview. So simply put, Mukai simplifies the application use of quantum computers, and thereby it accelerates quantum computing adoption. So the fact that you're attending today says you're probably aware of quantum computers and probably have some interest in what they might do for you. Many of us are excited about that. And of course, there are some real challenges to delivering the promise, the potential of quantum computing for real world problems. One of those is we have to scale to real world problems. Another is there really needs to be subject matter expert APIs, not just very low level APIs, because we need to be able to avoid the lengthy and costly learning curve and rework that happens if you program it at a low level. Second, we need to port to a lot of QPUs because there's a lot of uncertainty about which ones are ultimately going to be the best for which problems. And also, we need to deliver strong classical performance now, prior to quantum advantage. And we also need to deliver strong early hybrid quantum classical performance once we have quantum advantage. There's a big need to accelerate retargeting of applications from purely classical mode to hybrid quantum classical mode. And we also want to minimize technological risk, i.e. we don't want to be locked into a particular QPU. You want to be able to shift because all of us want to be able to run on the best, fastest QPU at any point in time as that unfolds. So in that context, the value of Mukai is as a bridge to quantum for subject matter experts and app developers, meaning you can solve problems on quantum computers with no quantum programming expertise. You can transparently benchmark the same problem implemented the same way on leading QPUs as well as very strong classical solver. And you can solve big problems with near-term small QPUs. As a developer, you only need to learn a few simple API calls that are based on familiar, consistent concepts like constraint optimization and graphs. You'll have transparent access to diverse QPU and CPU resources today. December 4th, we support Rigetti, D-Wave, and IonQ QPUs in our released product. And we have that many again in the pipeline coming soon. You can solve the same problem with no changes other than a pointer to the processor you want to use on classical CPUs. And you can actually get superior performance using those same APIs. So in a nutshell, that's what Mukai does. So let's kind of take from another perspective. Let's put ourselves in the perspective of someone who has an application. I have reason to believe that a piece of that application is quantum amenable. I could get benefit from a quantum computer. So what do I do? For sake of argument, say I want to run on a gate model quantum computer. What do I do? Well, actually, it's a pretty long list. Even if I already have intuition that a piece is quantum friendly, quantum amenable, I'm probably going to want to shrink, reduce, simplify that before trying to map it to a quantum processor. I'll do that mapping. to an abstract quantum processor. But then I have to map from the abstract quantum processor to the physical quantum processor, which has certain physical realities and perhaps foibles. Also, today's QPUs have noise, they have errors. I have to know how to deal with those things to use them effectively. Jumping over here to the right column, QAOA and VQE are fairly well-known algorithms for solving optimization problems on gate model quantum computers. If I'm going to use one of those for a particular problem, I have to calibrate those the algorithms for my problem in the QPU I'm running on. That's another piece of work. And maybe I'll just jump down to the one in the lower right-hand corner here. In the last 12 months, 7 new QPUs have come out from various vendors. So if I want to stay at the state of the art, I need to do these steps for a new QPU every 7 weeks. So that's almost a full-time job itself. That's like painting the Golden Gate Bridge. So that's a tremendous amount of complexity to stay on the quantum trend. What Mukai does instead is say, no, we're going to deal with that complexity for you. We are quantum computing experts. We can get into that depth. You don't have to be. And what we focus on is a couple of things. So here's our constrained optimization API. And to do that, to use that, you pass constraints and an objective function. These are things that if you're doing constrained optimization, these things are very well known to you. We have a kind of specialized API on top of that, which is specifically for graph analysis. And so and Mark will talk about that later. The point is that underneath the covers, that's still constrained optimization. So it converts into the constrained optimization API and calls that. So it depends on the significant amount of work we've done under that API to solve those problems well on CPUs, on annealing QPUs, and on gate model QPUs. So that's what Mukai does to simplify and offload that complexity from you as somebody wanting to move an application to a quantum computer. What does that buy me if I'm using Mukai? Well, our experience and the experience we hear about from early users is that to use the existing toolkits takes anywhere from 4 to 16 months. If I start out as I'm not a quantum computing expert, to the time I have an application running well on a quantum computer is 4 to 16 months. Some of what goes into that is, even if I know quantum mechanics, I may not know that much about quantum computing specifically, so I have to learn that. Then I have to learn about programming a quantum computer. And then I still have to pull out that piece of the problem that's quantum amenable. I still need to express it in these terms. And I need to run it, tune it, rerun it, retune it, etc. What we hear is 4 to 16 months for that to happen. With Mukai, that's a week. You learn the API, simple, well-known concepts that you're already familiar with. You define your problem, process it, you get results back in the same terms, the same level of concepts you submitted them, and you get on with life using a quantum computer. So a few practicalities. Mukai is a constrained optimization cloud service, delivers strong performance today, running purely classically, and we're preparing for strong performance tomorrow in a blended quantum classical form. And you get this from subject matter APIs. I've already said constrained optimization and graph. If you're interested in performance details, you can look at the archive paper about what we've done with graph partitioning. How big a problem do we solve today? So far, we've been up to 110,000 variables and 8,000 constraints. That ran purely classically. As I mentioned before, we have support for Rigetti, IonQ, and D-Wave QPUs today. If you're running on one of those QPUs today, you're limited to the size of the QPU. We realize that's a significant restriction, and we have key developments underway, so watch this space for that. And if you want to look at the documentation, that's available on the web. So now I want to shift gears, and Raouf will take it and present the use of our constrained optimization API.
Hey, thank you, Steve. Hello, everyone. My name is Raouf Dridi, and I would like to introduce you today to our API for solving constraint optimization problems. And my plan to do so is using a simple example. And you see I'll be solving the example first classically and then quantum mechanically. Using for backends here, we have D-Wave Advantage, D-Wave 2000Q, Rigetti, and IonQ. And I also will be using popular quantum algorithms, quantum annealing, VQE, and QAUA. So first, the example. So this is an example of power grid optimization, where we have a number of plants and to be assigned to n regions, such a way we minimize the cost of the inter-plant transportation. Let me show you a picture here. So here in this example, we have n squared binary variables representing whether plant P is assigned to a location I. And the objective function here is the product of two quantities, the cost of transporting 1 unit of energy from a given location to another, and the number of units of energy to be transported. So mathematically, this is what you have. We have a constraint optimization problem. The two set of equations here are the constraints, which ensure that only one facility is assigned to each location. So people familiar with this type of mathematics will recognize this is just an instance of quadratic assignment problem. So and the example was taken from the paper I'm pointing to here. Now that's okay if you don't really fully understand the example. That's not the goal here. But what I want you to appreciate is this is a constraint optimization problem where we have a cost function to minimize a certain number of constraints to satisfy. And I'll be solving this using Mukai. So for example, when n is 3, n being the number of plants, the objective function is a 9 by 9 matrix. And the constraints come together and form a 6 by 10 matrix. 6 because we have 6 constraints, and 10 that's 9 plus 1 because we append the right-hand side of constraints. This is a common practice in constraint optimization. Now, the way I'm solving this is using a simple and familiar Lagrange multiplier formulation, where we have a Lagrange multiplier alpha, which taxes you whenever you violate a constraint. So this is the description of the example and the mathematics behind. I'd like to go back to Mukai and solve the problem. So the first thing I do is I start by importing the API, and then I'll be solving the example classically first. And I do this using one function, and this is the only function I'll be using throughout my demo, sample Lagrange optimization. And I call this function on my objective function and the constraint matrix, the two matrices I introduced earlier. Okay, so I run this, I get my solution, and the solution is simply, well, I get the optimal solution of the problem. I get something like the plant 1 is assigned to region 1 and so on. What I can do also is tracking the evolution of the Lagrange multipliers throughout the process. And for instance, I can see at the very beginning my initial set of Lagrange multipliers. I have 6 of them because I have 6 constraints. and I can see the constraints are not satisfied. Now, if I go all the way down, I see all my constraints are satisfied. And this is the final set of the Lagrange multiplier. So this is a tiny baby example for QCI, QBSolve, but the goal here is to demo the quantum solvers. So this is what I will be doing for the rest of my talk. For the rest of my talk, I'll be solving the very same constraint optimization problem, now quantum mechanically, and we will see we get the same solution, but also the same nice convergence behavior we have here. Okay, so I'll start with D-Wave. For D-Wave, I have the option between bracket advantage and bracket 2000Q. I'll start with the bracket advantage. And the way I do this is exactly the same as before. So I'm calling the same function here with the exception of the new parameter I'm introducing here, which is sampler. So I set sampler to my bracket D-Wave advantage and let this run. And I get the same solution as before. This is me checking against the solution I obtained using QCI QBSolve. Now the same is true for the bracket 2000Q. Again, the same syntax with the sampler now set to bracket D-Wave 2000Q. That's the only thing I did here. And I get the same solution and the same behavior as before. In particular, I see the constraints are all satisfied at the end of the process. Now moving to Rigetti. Again, it suffices to set the sampler to bracket Rigetti and call my sample Lagrange optimization with this particular sampler. I'll let this run. And again, I'm doing the same checking here. I get the same solution, the same behavior as before. Now, people familiar with this type of hybrid algorithms, we know that there is an ansatz under the hood, and in this particular case, by default, VQE is used, and here is the generic ansatz we have used. Now, if you would like to use QA, then again, it suffices to set the algorithm parameter to QA and run again the same line, which I do here, and then I compare. I'm getting the same answer again. So everything I said about Rigetti holds true for INQ. In particular, setting the sampler to bracket INQ will solve the problem on using VQE on brackets INQ device. I compare again, I get the same answer. Now, my last example, and this is my last example, I'll be, and the goal here is just to present some of the parameters the user can play with and tweak. For instance, you have the parameter algorithm, but also the parameter optimizer, which stands for the classical optimizer. So you can choose the classical optimizer you'd like to use, but also the options you want to pass to the classical optimizer. And of course, you have access. You can also set the circuit depth and also the number of shots and so on. And of course, when I run this, I'm getting the same answer. Now, to conclude, if you want to learn more about the API and the features I presented today, you can go and check this website here, and which takes you to our documentation page. In particular, you can find examples, more examples. But also you can also find more information about the type of arguments and parameters you can tweak and tune. For instance, here these are the parameters I just introduced: algorithm, optimizer, and so on. This is for hybrid algorithms, but also we have the same thing for DOF and quantum annealing. For instance, the number of reads and the chain strength and so on. So this is the end of my demo. I thank you very much, and back to you, Steve.
Excellent, thank you. So Raouf has shown us a strong constraint optimization capability callable by SMEs that gives excellent results either purely classically or hybrid quantum classical. Next, we have Mark Wanger presenting about community detection, a higher level and more focused API that under the covers is constraint optimization, but solves a higher level problem that early users are telling us is high value. So Mark, off to you. Mark, you need to unmute, I think.
There we go.
Yep, now we got you.
Oh, sorry. There we go. Mark Wanger, Director of Application Development here at QCI. I'm going to talk about quantum community detection, which is a graph analytic that's fairly new. The seminal paper was written by Newman and Girvan back in 2004 for finding and evaluating community structure in networks. Here's a simple schematic where you have a bunch of nodes in a graph that are connected by edges. You want to identify the communities, the nodes that are densely connected, and the connections across communities should be much less dense. A standard example that's used and presented in this paper is called a karate club network, which is 34 members of a karate club and their associations. The key concept they introduced was modularity is a measure of how well you've identified the communities. And they typically are implemented algorithms using local optimizations. We based our work on a more recent paper published in 2019 by some researchers at Los Alamos, which set up a global optimization process to find the absolute best answer. And that's amenable to setting up as a QUBO and therefore solving it in quantum hardware. An example they present, which may be more interesting to you guys who are viewing this presentation, is analyzing a small protein, looking at the interactions between the electrons orbiting around each atom. And so each dot here represents an atom, and the community detection identifies each community, which turns out to be an amino acid. So there's 7 amino acids making up this protein molecule. And the modularity is a unitless number between 0 and 1. The modularity that's found for this protein is 0.76. So that's a very high modularity, which is typical of physical science type things. The human the karate club modularity is on the order of 0.4, so much less, because humans are a little messier than atoms are. Okay, so to go to the code, I'm going to start and use Network X, which has the karate club built into it, karate club graph, and we can have a quick look at that. So I printed out the edge list, so you can see there's each node is numbered, so 0 is connected to 1. This dictionary here is empty. It could have a weight, so that it could be weighted edges, but in this case, they all have a weight of 1, so it's basically an unweighted graph. And you can see the visualization of it, similar to what was presented in the Newman and Gervin paper. And Network X also has a community detection algorithm built into it. It's one of these locally optimizing algorithms. So every time that it starts with all the nodes in one community and it breaks them, it splits one of the community in order to optimize modularity on each step. So the first step, it got two communities with a modularity of 0.36. And you'll notice that node 2 is separated from its nearest neighbors 0, 1, and 3. Once it splits, it can never recombine, and that turns out to be a fatal error right at the start. If you're trying to find the globally optimal solution, because 2 really wants to be in with 0, 1, and 3. In this case, then gets 3 communities, and the modularity actually decreases to 0.34. 4 communities back up to 3.6. 5 communities is the maximum at 0.401. And then 6 and 7 communities, the modularity starts to decline. So as far as the Network X algorithm is concerned, 5 communities is the optimal solution with a modularity of 0.401. Now we have the Mukai version, where we're going to call QCI Network X community detection. Pass in the graph, the number of communities I want to find, and I only want the top solution. I'm going to do that for 3, 4, and 5 communities. And so this is running in real time, hitting our AWS server to get the solutions. For 3 communities, the modularity is 0.402, so we already beat the Network X modularity by 0.001. And you can see that 0, 1, 2, 3 are all together, so 2 wants to be with his neighbors. The optimal solution, which matches what was reported in literature, is for 4 communities with the modularity 0.4198. And we tell it to search for 5 communities. It comes back, says, sorry, I only found 4. This last one here is empty. And of course, the same modularity and exactly the same communities are found. And here's a visualization of the 4 different communities that are found for the Karate Club network. So that's fine, but in general, why are these individuals connected? Well, that information is lost for the Karate Club. But typically, a lot of real-world networks are what are called bipartite networks. So there's 2 different kinds of nodes. And nodes of a given kind don't connect. They only connect to nodes of the other type. And 4 years after the first paper, this paper by Barber was published in 2008, which is specific for detecting modularity and communities for bipartite networks. And the classic example is the Southern Women Network. So this is from the 1930s. There's some data. 18 different women went to 14 different meetings in different combinations. So you want to find the communities that are represented. So each woman is only connected to the event she attended, and each event is only connected to the women that attended that event. And they report the optimal modularity. Barber reports the optimal modularity is 0.34554 down here in the bottom. And so, again, Southern Women is built into Network X. And so we can visualize what, so the nodes in the network, they're women that are assigned to the bipartite 0. So they're all in the 0 grouping. And then the events are assigned to the 1 mode or grouping for the bipartites. And the edges only connect a woman with the meetings that she attended. So Evelyn Jefferson attended event 1, event 2, event 3, event 4, etc. And again, it's an unweighted graph. There's no weights involved. And here's a visualization of this network. So you see all the women on the left-hand side, the events on the right-hand side. The events only connect to the women and vice versa. Now, as Steve was saying, this is really a constrained optimization problem. I was hoping to just be able to call Mukai the same way as I did for the single type of node unipartite graph. but we're still working on the infrastructure a little bit. So this is the under the covers part that you would have to write yourself if you want to do some community detection. We didn't provide that facility, and then it's sort of nice because you can see that under the covers, what we would do is we calculate the modularity matrix, which is the objective function B. We calculate a constraint matrix, which is constraint matrix C. We normalize that, and then we don't, in this case, you don't really need to use a Lagrange optimization. Using a single Lagrange multiplier of 1.5 is good enough to get the correct solution. So I can run this. Oops, this one. And again, I'm doing this in real time, calling our solver. And you can see for 3 communities, it found a modularity of 0.345. For 4 communities, it found the 0.3455 instead of 5.2. So there's a very small difference between 3 communities and 4, but 4 is the optimal. 5 also, if I ask it for 5, again, it only finds the same 4. And yeah, the subject matter expert would decide whether that small modularity difference is more meaningful, or perhaps 3 communities are more meaningful. But then you can see the final result is number of women, and the women are connected to the events and grouped together into the different communities. And that's the end of my presentation. So let me hand it back over to Steve now. Thank you.
Excellent, Mark, thanks. So we've seen Raouf demonstrate the constrained optimization capability via SME accessible API. Mark has taken us to a higher conceptual level with community detection. In the interest of time, we barely scratched the surface of each of these capabilities. So if you have detailed questions, please follow up. Raouf and Mark understand deeply how to use these capabilities for real world problems. So to summarize, we've demonstrated how to use MuKai to solve real-world constrained optimizations problems, exploiting the power of quantum computers. Today, MuKai delivers a constrained optimization cloud service via subject matter expert APIs, featuring strong performance today classically, and preparation for strong performance tomorrow, blended quantum classical. So in terms of next steps, here's where we're hoping you have a role to play. Do you have high value optimization problems you need to solve better or faster? Are you ready to start using quantum computers with minimal time invested? Do you want to see if quantum techniques accelerate your classical execution? You want to compare the performance of multiple QPUs for your problem? We have quantum experts, Raouf, Mark, and others. You can brainstorm with, and we have free trial licenses to get started. You can contact John Dawson, who's on the call here, or also you could contact him afterwards at the email address. And with that, we'd open it up to any questions you may have.
I have a question that I'd like to ask. I'm very naive about this computer hardware in terms of quantum computer. I heard a lot about D-Wave, for instance, and you had the possibility of doing quantum annealing on D-Wave system. Are there any speed up obtained using that kind of computer, or even using QCI's computer? What are the kind of speed ups that you can get if you switch over to a quantum system? It seems to me that this is still in its formative stage, because you're talking about algorithms used on classical computers and so on. So what is the status of the technology now?
Yes, and you summarized it accurately. There are many people working very hard on a variety of QPUs to use them to their best advantage. To my knowledge, so I think probably everyone is aware of the Google quantum superiority result from October of last year. And I guess I think that was quantum superiority. It's a problem that it is not, I mean, it's a math problem. It's not, it doesn't have any real world value, or its real world value is very obscure. I'm not aware that anyone has used a QPU to deliver superior performance on a real world problem yet. So what we are doing, I mean, and we know that there is a huge amount of effort to deliver such capability, to what's called quantum advantage, a performance benefit on a real world problem. So there's a huge amount of work to do that. And so we are preparing ourselves and Mukai, and by implication, our users, to be able to take advantage of that quantum advantage when it is delivered. When that will be, we don't know exactly. Which vendor it will be, we don't know exactly. But our goal is to have the software ready so that you can have an application ready, so that when quantum advantage is delivered, you can exploit quantum advantage very quickly.
So it doesn't matter who delivers the hardware. Say Google comes up with a hardware that can do the task. You can move Mukai over to Google computer.
Exactly.
And have quantum advantage as well.
Exactly.
Okay, thank you.
So I had some questions about the algorithms themselves. Okay, so you are saying that in principle, you have some sort of platform where you can use either a classical computer or different, quantum computers. And you're saying that even in the classical case, okay, your optimization, your constraint optimization problems are more efficient than others, okay? So my question is, there are series of problems of interest in physics, for example, where you can transform the problem into a constraint optimization problem. For example, calculating the ground state of the Hubbard model, okay? So, you know that these problems are NP-hard, and you know that the best classical computers we have today allows you to essentially answer that question for a certain lattice size for the Hubbard model. So when you're saying that your classical algorithms, I mean, if you're using your platform, for example, and if I wanted to apply this to the Hubbard model, how far can I go already at the classical level? Then we can discuss whether we are using, the quantum platforms to even get some speed up. So what kind of answer you can give me? I mean, for example, I can tell you that, if you're trying to solve the ground state of the Hubbard model, it depends, what kind of algorithm you want to use. And of course, the most efficient algorithms that you can use are quantum Monte Carlo, but quantum Monte Carlo suffer from a sign problem. So you have to do something. So can you tell me, for example, how efficient is your platform for these kind of problems, for example?
Right. So let me answer partly, and maybe I'll ask Raouf to answer partly as well. So the best results we get are for constraint optimizations problems that are discrete, meaning that the answers are, one of 6 or 12 or 43 problems. We are also, we feel like that's where our best advantage is. We can also solve continuous problems. We feel like we don't have as much, we're not as strong there relative to the best classical solvers. The other thing I would say is we have run some problems. I put up a URL about our graph partitioning paper. That is one problem, and we feel like we've done well on that. There are many other problems, and we continue to work on performance, both of the kind of the common constraint optimization core of our product, and we continue to work on performance for each algorithm, like graph partitioning. But we certainly have not optimized everything, all of those various algorithms yet. So, we still have some to learn about which algorithms are most important, which, like the hover problem you said, what does that look like? Do we do a good job of that? If not, why not? What can we change to do better? So those are my thoughts. Rauf, you may have deeper understanding there.
No, I agree, and I can't really answer your question without trying the example. So because each problem is different, so you cannot really generalize what you see in for a particular instance or particular problem to completely different problem. But what I can say is this is what Steve just mentioned. We have done some benchmarking. Some of them are published, and some are coming soon. But these are for graph partitioning, for QAP coming soon. So it's really depend on the problem you want to solve. But the best way to tell is go ahead and try it and see yourself what type of benefits you get.
Thanks. So the other question is more on, just you show some examples, and I agree, probably, for discrete variables, it's better. But, I mean, all these quantum computers, they have errors, okay? And I'm surprised that, whenever you were showing all these examples and you were getting true, and you were getting all these, similar kind of conversions, I mean, where do errors show up in the quantum platforms? There should be some errors somewhere.
Yeah, but in this case, there is a noise mitigation, but it's not really as important as you may think, because these are small examples. So you start seeing much more serious problems as you go for bigger problems. But we do have, there is a noise mitigation in the process.
I see, but you must probably be selecting also the qubits that you are using in the computer. Or you mean, whatever set of qubits that you are choosing, you get exactly the same performance. Because, I mean, we can play with an IonQ, for example, okay, with whatever. And when we play and we put any algorithm there, okay, I mean, of course, the performance is not the same. You have to choose, not all qubits are equal. Let's put it this way.
Qubit allocation, yeah, of course.
Yeah.
No, I agree. This is part of the process as well. So you're probably familiar with this notion of noise mitigation, which does all this type of calibration for you.
Right.
But this is you start seeing more problems as you go for bigger problems. For the time being, we can always mitigate and and fix any problem. We know how to do so, right?
Don't we also, Rauf, don't we also deal with this by doing a lot of shots and just getting the best answer?
Yeah, exactly. That's part of the things we do. Yeah, exactly. But this is, it's a whole industry, it's mitigation, right? So there are a certain number of techniques we apply, and in theory, we solve the problem.
And hopefully that's part of the value we add, is that, we deal with this kind of stuff so that the end user doesn't have to.
Right, and we're we're already talking with customer or companies and external groups that are experts in how to use QPUs most effectively, how to tune them most effectively, how to mitigate errors. We're not going to be the world's expert in all those areas, but we are going to work with the world's experts in all those areas, and we'll integrate the best known techniques into Mukai so that we're able to deliver the best possible answers. And really, we see that as part of the benefit. I mean, we think that there's a certain cadre of people who really want to be, in the middle of the quantum processor and understanding those, the noise and other issues, and that's great. And there's another set of people who say, I just want to use the quantum computer. I have a problem to solve. And for those people, we think that's part of the value we deliver is we figure out what's the best error mitigation. What's, how do we use, how do we use noise aware compiling, things like that, so that you can just solve a problem. You don't have to think about that.
I see.
So if you want to follow up, we'd be happy to, talk more about how to map a particular problem effectively to Mukai and see what results we get, that kind of thing.
Okay, thank you. So the interface that you're using is Python. I mean, it's that's the interface that whoever uses that Mukai will face with Python.
Yes.
Okay. I see. And what if, for example, I mean, I come and I telling you, well, I have a quantum computer. I have an ion trap quantum computer. So it's easy to incorporate that computer in your sampler, whatever you call the things, or you need to understand, do experiments, or do something.
Well, part of the answer would be if you came back and said, I have an ion trap computer, and it's from Rigetti. Sorry, it's from IonQ. Excuse me, I misspoke. Then we would say, yep, we know how to handle those because we already do that. If it's from another vendor, then we're talking with other vendors. We may already be talking with the one that you have access to. If it's one that you created yourself, then we'll have a lot of questions about what software you have and how to talk to your QPU most effectively.
I see. Thanks.
Mm-hmm. So there was a message from Alex Pothen on the chat. It said, could you say something about the runtime behavior with problem size for QAP and for the community detection problem?
Yeah, I can take the community detection. We running a bigger problem. For example, there's a pretty standard graph of criminals and the crimes they committed. That's about 1,300 nodes altogether, and we can solve that problem, get the optimal answer in a couple of minutes in our classical solver, which is a 96 core machine that's hosted by AWS. And that, of course, is too big currently to run on a QPU, but that's part of what we're working on for the future is solving big problems with small QPUs. We've also solved in the finance world, we can set up they typically deal with continuous variable problems. So we have to do some binary encoding in order to calculate floating point get a floating point answer with our binary variables that are underlying it. in size. We can set up problems that involve 20,000, 40,000, 60,000 binary variables. Problems of that size are going to run for an hour or two on our server, but we can get to the number of, say, we use 20-bit encoding, so there's 20 binary variables for each floating point number. So that's not as good as a 64-bit double precision, but to the extent that we check the first couple of digits, we'll match what CPlex or Gurobi's the answer they get for a non-NP hard problem. Once it gets to NP hard, then typically Gurobi or CPlex can't give you an answer. So even if you have to wait for a while, it's better to wait and get an answer than to not get an answer to your problem.
Yeah, I can also say something about QAP. So this is underway, and we hope with a paper will come out very soon. Essentially, because there are different ways to do so. As QAP has a constraint optimization problem, so you may think about it. There are different ways to solve the problem. So, for instance, in the context of QA, maybe you would like to customize the mixer operator in a way it captures the constraints. So the evolution within QA would be inside the feasible region, right? You are feasible all the time, all the way to the solution. And you like to compare this with the other ways you solve an optimization problem. So the answer is this is work in progress, and hopefully we see a paper very soon. So we have some nice interesting observation there.
So are there others with high value optimization problems?
So can you solve problems, I mean, even classical problems with directed graphs?
So when you say problems directed, what type of problems?
For example, neural networks with directed graphs, where, the probability to go from one node to the other, essentially I to J is not the same as J to I.
So yeah, provided you define the problem as a binary optimization or a constraint optimization, then you can go ahead and solve it. Now, if you have a continuous variables you'd like to train, it's not strictly a binary optimization problem. It's an MIP problem, right?
Right. No, these are not necessarily binary, but they are discretized. You can have in each node.
Then in this case, yes. So the answer is yes. So if you discretize, you go ahead and brutally discretize the problem, then then this is a binary optimization. You can solve it.
Also, for in the case that the directed graph is only made up of one type of node, a unipartite directed graph, you can also consider that as a bipartite graph, where the two groups are the start and the end, or the in and the out. And so each node is represented twice, once as the start of the directed graph, or the directed connection, and the other node is or the other group of nodes is the end of the directed graph. So you double the number of nodes, but then you can treat it as a bipartite graph.
I just want to add, going back to MIP and discretizing the problem. Maybe you may want combine QB solve, QCI QB solve, or Makai with your favorite continuous optimizer, and and then in the same way you train QA. If you're familiar with the inner working of QA, then you can do so. So without discretizing the problem, which might, because when you do so, you might lose structure. Or and then the idea is, combining this with one of the popular continuous optimizers out there. And the picture of QA, it's a good example of how actually the two type of solvers talk to each other.
So yeah, and those are kinds of things that we're keen to investigate. So if you have problems in those veins that are high value to you, we'd like to understand those and kind of talk through that a little bit more.
I got a question. So you mentioned you were trying to solve a large problem using the smaller QPU. I would assume using some multi-level algorithm or divide-and-conquer algorithm. So my question is the algorithm going to be problem specific? Like you are going to need different algorithm for different graph problems, or you can use one universal algorithm for all kinds of cubo or all kinds of graph structure?
The short answer is we don't really know yet. We've done some experiments, but not nearly enough to have a comprehensive view of what's going to work where. We do expect that it will take a variety of techniques to solve, to have a robust capability that works for lots of different problems. But exactly which ones are going to work on which kinds of problems, we just don't know yet.
Okay, thank you.
But again, if that's a problem that you see as high value for you, if you have examples that you could share with us that would be valuable for you, we'd love to hear about those. Well, if there are no more questions, I guess I'd mention again that if you're interested in a trial or a colleague that may be interested in this, feel free to forward our information to those, and we're happy to work with people on trial basis. And obviously we're connected well with David and the Quantum Science and Engineering Institute. So please feel free to contact us afterwards if something comes up.
Yeah, I mean, I may, there is a problem that is related to brain dynamics, okay? That we have problems because it's NP hard, okay? But we have some problems simulating. This is classical, it's not quantum, okay? Of course, you can make quantum, but that's not the point. The point is that I am thinking I am thinking how to convert it to an optimization problem, because it's a cellular automata. But I have to think how to convert this into an optimization problem. But that is something that could be interesting if you have a more efficient way of simulating these things, scaling up. That could be an interesting thing. And there are experiments also related to these things, with electrodes and things like that.
Right.
So So yeah, but I have to think how to do this kind of conversion.
That'd be
Maybe
great.
I can tell you what the problem is. Okay, maybe I can, I can contact you, and maybe some of you realizes how to convert it into an optimization problem. But it
Yeah,
can be
absolutely.
discretized. It can be discretized. A directed graph. It's a stochastic cellular automata. It has some features which are interesting. But and we have simulated those things. Okay, we have simulated those things, but it's hard to scale up these simulations. Experiments are performed in something like 500 nodes. We can simulate of the order of 100. Okay, so yeah, I can contact. I don't know who is the best person to contact. Maybe I can ask David afterwards, but yeah, I can contact and I can tell you what is exactly the problem.
Yeah, that'd be great.
Yeah, Steve, can we get copies of the slides that were presented?
Yeah. I'll
Yeah,
send
and then
those to you in a few minutes.
I can share the slides and your recording with those who were not able to attend. And then, if you don't, I think, did you put contact information somewhere, or can they find that on your website?
I don't think I did. So
Okay.
actually, the dirt simple thing is, I mean, am I sharing my screen?
Yeah, we can see your.
So
PowerPoint.
so for instance, I'll just put mine here, but we use the first initial last name.
Okay, excellent. So you can certainly contact me as well, and then I can give you Steve and his team's contact information as well. And if you're, from outside of Purdue and you want copies of the slides, let me know, and I can get those to you as well. So excellent. Thanks, Steve, Bob, and all your team, Raouf, Mark. Excellent work, and thanks so much for joining, and thanks to everyone who participated today.
Thank you very much.
Yes.
All right. Take
Thank you
care,
for your
everyone.
time.
Have a great weekend. Stay
Thank
safe.
you.
Cheers.
Yeah.